Hey everyone, today we will be exploring this full-stack PERN AI recipe generator application we built. This is a complete AI-powered cooking assistant with user authentication, smart pantry management, AI recipe generation using Google Gemini, meal planning, shopping lists, and much more. So let's jump right in and see what this app can do. Alright, starting with the login page here, we have this clean, modern design with a beautiful gradient background. On the left side, we've got the login form with the project name and tagline, Your AI-Powered Cooking Assistant. The form itself is pretty straightforward. Email and password fields with nice emerald green accents that match our app's theme. And at the bottom, there's a link to sign up if you don't have an account yet. Let's quickly show you the sign up page. This follows the same design pattern as the login page. The form here has fields for name, email, password, and confirm password. The form has validation built in, so if you try to submit with mismatched passwords or invalid email, it'll catch that. Once you sign up successfully, you're automatically logged in and redirected to the dashboard. Now, before we dive into the features, let me talk about the tech stack we're using here. This is a PERN stack application. That stands for PostgreSQL, ExpressJS, React, and Node.js. On the backend, we're using Node.js with ExpressJS to build our RESTful API. For the database, we're using PostgreSQL hosted on Neon, which is a serverless Postgres platform that's perfect for modern applications. We're using the PG library to connect to our database and execute queries. For authentication, we're using JWT with bcryptjs for password hashing. This ensures secure user authentication throughout the application. The really exciting part is the AI integration. We're using Google's Gemini 2.5 Flash model through the Google Gemini SDK. This powers our intelligent recipe generation, pantry suggestions, and cooking tips. On the front end, we're using React with Vite as our build tool. Vite is much faster than Create React App and gives us a better development experience. For styling, we're using Tailwind CSS version 4, which allows us to create this beautiful modern UI with utility classes. Let's go ahead and log in now. Perfect. So now we're on the dashboard, and right away you can see this clean, organized layout. At the top, we have the main navigation bar. On the left is the AI Recipe Generator logo with the chef hat icon, which takes us back to the dashboard at any time. On the right side of the nav bar, we have navigation links to Dashboard, Pantry, Generate Recipe, My Recipes, Meal Plan, Shopping List, and Settings. And on the far right, we have the User Profile dropdown showing the currently logged in user's name. The dashboard gives us a great overview of our cooking stats. We have 3 stat cards at the top showing total recipes, pantry items, and meals this week. Below that, we have these beautiful quick action cards. The first one is Generate Recipe with a gradient emerald background. This takes us directly to the AI recipe generator. The second one is Manage Pantry for adding and tracking ingredients. Scrolling down, we have 2 sections side by side. On the left is Recent Recipes, showing our latest saved recipes with cooking time. On the right is Upcoming Meals, showing our planned meals from the meal planner. Both sections have View All links for easy navigation. This dashboard is pulling data from multiple API endpoints. We're making parallel requests to get recipe stats, pantry stats, meal plan stats, recent recipes, and upcoming meals all at once using promise.all for optimal performance. All right, let's click on Pantry in the navigation to manage our ingredients. Perfect. So now we're on the Pantry page where users can manage all their ingredients. At the top, we have the page title and description, along with an Add Item button in emerald green. Right below that, notice this alert box. This shows items that are expiring soon within the next 7 days. This is a smart feature that helps reduce food waste by alerting users about ingredients they should use quickly. Below the alert, we have a search and filter section. On the left is a search bar where we can search for specific ingredients. On the right, we have category filter buttons: all, vegetables, fruits, dairy, meat, grains, spices, and other. These buttons dynamically filter the items as we click them. The pantry items are displayed in a beautiful grid layout. Each card shows the ingredient name, category, quantity with unit, and expiry date if set. Items that are expiring soon have an amber border to make them stand out. There's also a running low badge for items marked as low stock. Each card has a delete button in the top right corner that appears on hover. Let's add a new item to the pantry. When we click Add Item, a modal pops up with a clean form. We can enter the ingredient name, quantity, unit. There are multiple unit options like pieces, kilograms, grams, liters, cups, tablespoons, etc. We can select a category, set an optional expiry date using a date picker, and mark it as running low with a checkbox. On the back end, this is using PostgreSQL to store all pantry items. We have a pantry items table with columns for user ID, name, quantity, unit, category, expiry date, and is running low. The database uses foreign keys to link items to users, and we have indexes for fast queries. Let's fill in the details and add a few items. Great, now we have several items in our pantry. Notice how they're organized and easy to browse. The search and filter features make it simple to find specific ingredients even when you have a large pantry. Now let's navigate to the most exciting feature, the AI recipe generator. All right, so this is the AI recipe generator page. At the top, we have this beautiful header with a sparkles icon and the title AI recipe generator with a description. The page is split into two main sections. On the left, we have all our input controls. On the right, the generated recipe will appear. Let's start with the ingredients section. First, we have this checkbox that says Use ingredients from my pantry. When we check this, the AI will automatically include all our pantry items when generating the recipe. Below that, we can manually add additional ingredients. Just type in ingredient name and click the plus button or press enter. Each ingredient appears as a tag that we can remove by clicking the X button. Now let's talk about the preferences section. First, we can select a cuisine type from a dropdown. We have options like Italian, Mexican, Indian, Chinese, Japanese, Thai, French, Mediterranean, American, or any. Next, we have dietary restrictions. These are toggle buttons for vegetarian, vegan, gluten-free, dairy-free, keto, and paleo. We can select multiple restrictions and they'll turn emerald green when active. Below that, we have a serving slider that goes from 1 to 12 people. The current value is displayed above the slider. And finally, we have cooking time preference with 3 options: quick, under 30 minutes, medium, 30 to 60 minutes, or long, over 60 minutes. Let's select some preferences. I'll check Use ingredients from my pantry, select Italian cuisine, choose vegetarian, set servings to 4, and select medium cooking time. Now when we click the Generate Recipe button, here's where the magic happens. On the back end, we're making a post request to our Generate Recipe API endpoint. The back end receives our preferences and ingredients. If we selected Use Pantry Ingredients, the back end queries the Postgres database to get all our pantry items and adds them to the ingredients list. Then we're using the AI model. We construct a detailed prompt that includes all the ingredients, dietary restrictions, cuisine type, servings, and cooking time preferences. The prompt asks Gemini to return a complete recipe in JSON format with specific fields. Excellent! The recipe has been generated. Look at this beautiful layout. At the top, we have the recipe name and description. Below that, we have badge tags showing the cuisine type, difficulty level, and any dietary tags like vegetarian or gluten-free. We can see the total time and servings with nice icons. Then we have the ingredients list. Each ingredient shows the quantity, unit, and name with a little emerald dot bullet point. Scrolling down, we have the step-by-step instructions. Each step is numbered with an emerald circle, making it super easy to follow along while cooking. Next, we have the nutrition information per serving displayed in a grid: calories, protein, carbs, fats, and fiber. This is really helpful for people tracking their nutrition. And at the bottom, we have this card with cooking tips generated by the AI. These are helpful suggestions to make the recipe even better. At the bottom of the recipe, we have two buttons, Save Recipe to add this to our collection, and New Recipe to generate another one. Let's save this recipe. Perfect. We get a success notification saying Recipe saved to your collection. When we save a recipe, the backend creates a new entry in the Recipes table in PostgreSQL. But it's not just one table. We're using a relational database structure. The recipe data is stored in the Recipes table. The ingredients are stored in a separate Recipe Ingredients table with a foreign key to the recipe. And the nutrition information is stored in a Recipe Nutrition table. This normalized structure makes it easy to query and manage recipe data efficiently. Let's generate one more recipe with different preferences, and then we'll check out our saved recipes. This time, let me add some manual ingredients: chicken, bell peppers, and onions. I'll select Mexican cuisine, no dietary restrictions, 6 servings, and quick cooking time. Click Generate Recipe, and we get a completely different recipe. The AI is smart enough to create varied recipes based on our inputs. Let's save this one too. Now let's navigate to My Recipes to see our collection. Perfect! This is the My Recipes page where users can view all their saved recipes. At the top, we have a search bar to find recipes by name and filter drop-downs for cuisine type and difficulty level. All our recipes are displayed in this beautiful grid layout. Each recipe card shows the recipe name, cuisine badge, difficulty badge, cooking time, and nutritional information. The cards have a nice hover effect with a subtle shadow. Each card has a delete button that appears on hover. We can click on any recipe card to view the full details. At the bottom of each card, there's a View Details button. Let's click on one of these recipes. All right, so this is the recipe detail page. At the top, we have a back button to return to the previous page, followed by the recipe name, cuisine badge, and difficulty badge. The page layout is similar to the generated recipe view. We have the recipe description, time and servings information, the complete ingredients list, step-by-step instructions, and nutritional information. Now, let's check out the Meal Planner feature. This is the Meal Planner page, where users can plan their weekly meals. At the top, we have the page title and week navigation buttons: previous week, this week, and next week. Below that, we have a card showing the current week range. The main feature is this beautiful calendar grid. The header row shows the days of the week with their dates. The left column shows the meal types: breakfast, lunch, and dinner. Each cell in the grid represents a meal slot. Empty slots show a plus icon that we can click to add a meal. When we hover over an empty slot, it highlights in emerald green. For slots that already have meals planned, we see the recipe name in an emerald box. When we hover over a planned meal, a delete button appears to remove it from the plan. Let's add a meal to the plan. I'll click on the plus icon for Monday breakfast. A modal pops up showing Add Meal with the date and meal type. We have a search bar to find recipes, and below that, all our saved recipes are listed as radio button options. Each recipe shows its name and cuisine type. The modal has a nice scrollable area for the recipe list. Let's select one of our recipes and click Add Meal. Excellent. The meal is now added to our calendar. We can see it displayed in the Monday breakfast slot. When we fetch the weekly meal plan, the backend queries the meal plans table with a date range, joins it with the recipes table to get recipe names and images, and returns all meals for the week organized by date and meal type. Let's add a few more meals to our week to make it more complete. Great! Now we have several meals planned throughout the week. At the bottom of the page, we have stats showing meals planned, total recipes available, and the current week range. This meal planner makes it super easy to organize your week and ensure you're using your saved recipes effectively. Now let's check out the shopping list feature. Perfect. This is the shopping list page. At the top, we have the page title with an action button, Add Item. The shopping list items are displayed grouped by category: dairy, meat, produce, etc. Each item shows the ingredient name, quantity, and unit. We can check off items as we shop, and there's a delete button to remove items. We can add items to the shopping list using the Add Item button. This is useful for non-recipe items like snacks or household supplies. At the top, we have action buttons to clear checked items or add checked to Pantry. The Add Checked to Pantry button is really useful. It takes all the items we've checked off and automatically adds them to our pantry, then removes them from the shopping list. This creates a seamless workflow from shopping to cooking. Finally, let's check out the Settings page. This is the Settings page where users can manage their profile and preferences. We have tabs for Profile, Preferences, and Account. In the Profile tab, we can update our name. There's also an option to change our password. The Preferences tab is where we can set our default dietary restrictions, favorite cuisines, and default serving size. These preferences are used to pre-fill the recipe generator form, making it faster to generate recipes that match our tastes. Alright, so that's the complete walkthrough of this AI recipe generator application. The entire application is built with the PERN stack, PostgreSQL for the database hosted on Neon, Express and Node.js for the Backend API with JWT Authentication and Gemini AI Integration, and React with Tailwind CSS for the front end. So let's dive into the code and start building our PERN AI recipe generator app. Alright, let's start building. I have VS Code open here with an empty folder called AI Recipe Generator. This is going to be our project root. Inside, let's create two folders, Frontend and Backend. Let's start with the Frontend. Navigate into the folder. Now, to save time, I've already created a complete UI boilerplate for this project. We're going to clone it from GitHub and use it as our starting point. Let me clone the repository. Perfect. Now let's navigate into the front-end folder and install the dependencies. Great. All our dependencies are installed. This boilerplate includes React, React Router, Tailwind CSS, Axios, and Lucid React for icons. Now, before we run the app, let me show you how this project is organized. You'll see a well-structured folder layout. Let me walk you through each folder. Here, inside Components folder, we have all our reusable UI components, navbar and protected routes components. Inside Context folder, we have an auth.context.jsx file here that handles user authentication state. Right now, it's set up with dummy user data, but later we'll connect it to our backend. The Data folder has our dummydata.js file. It contains all the mock data we're using, dummy recipes, pantry items, meal plans, shopping lists, and user data. Inside Pages folder, all our main page components live. We have Dashboard, Login, Meal Planner, Pantry, Settings, Shopping List, Page components. Services folder contains our API service layer. Inside API.js, we have Axios configured with a base URL. And finally, the app.jsx. This is our main application component. Here, we set up React Router with all our routes, wraps everything in our off-context provider, and defines the navigation structure. Perfect. Now you understand how the codebase is organized. Let's run the app and see it in action. Let me start the dev server so you can see what we're working with. Here's our application. Let me give you a quick tour of what we've already built. Dashboard shows recipe stats, recent recipes, and upcoming meals. Dummy data for now. Recipe generator, add pantry ingredients, set dietary preferences, choose cuisines, and generate AI recipes. Currently using dummy data, we'll connect it to Gemini later. My recipes, browse saved recipes with filters and search. Recipe details, view images, ingredients, steps, nutrition info, and cooking time. Pantry, add ingredients, track quantities and expiry dates, and organize by category. Meal Planner, Plan meals for the week by assigning recipes to each day. Shopping list. Add items, check them off while shopping, and clear completed ones. Settings. Update your profile and dietary preferences. All of this is built with React, React Router, and Tailwind CSS. The UI is fully functional with dummy data, perfect for development without needing a backend yet. Now let's move on to building our backend. Let's set up our backend. Navigate inside the backend. First, we need to initialize a Node.js project. Perfect. Now open package.json and let's make a few changes. Change the main field to server.js. Now let's add our scripts for running the server. Great. Now let's install all our backend dependencies. We need several packages. Let me install them all at once. Let me explain what each package does. Google Gen AI powers our intelligent recipe generation, pantry suggestions, and cooking tips. bcryptjs for hashing passwords securely before storing them. Cores allows our frontend to communicate with the backend from a different origin. .env manages environment variables securely. Express, our web framework for building the REST API. JSON Web Token for creating and verifying JWT tokens for authentication. PG, PostgreSQL client for Node.js. This is the driver that lets us talk to our database. Now let's install NodeMon as a dev dependency. This will auto-restart our server whenever we make changes. Super helpful during development. Perfect. All our backend dependencies are installed. Now let's create our backend folder structure. Good organization is crucial for maintainability. Let me explain what each folder is for. Config folder holds configuration files like database connection, controllers for route handler functions, the business logic for each endpoint, middleware, custom middleware like authentication checking, models, database models, user, recipe, pantry item, meal plan, etc. Routes, API route definitions, utils, utility functions like token generation. Our backend structure is now set up. Now for the database. We're going to use Neon, a serverless PostgreSQL platform. It's perfect for modern applications because it's fast, scalable, and has a generous free tier. Let me open my browser and go to neon.com. Click Login. You can log in with Google, which makes it super easy. Once you're logged in, click Create a Project. Give it a name. I'll call mine AI Recipe Generator. And I will keep the default Postgres version. Choose your region. I'll select the one closest to me for better performance and click Create Project. Great! Our database is ready. Now we need to get the connection string. Click on this Connect button. You'll see the connection string here. This is what we'll use to connect our backend to the database. Copy this connection string. We'll need it in a moment. Now let's go back to VS Code and set up our environment variables. Create a .env file in the backend folder. Open it and add these variables. Now paste our Neon connection string into the database_URL field. Let me explain each variable. Port, the port our backend server will run on, we're using 5000. Database URL, the connection string for our Neon PostgreSQL database. JWT secret, a secret key for signing JWT tokens. In production, this should be a long random string. Gemini API key, your Google Gemini API key for AI recipe generation. We'll get this in a moment. And Node.env, the environment we're running in, development or production. Now let's generate a secure JWT secret. We can use Node.js's built-in crypto module to create a random secure string. Open a new terminal and run this command. This generates a 64-byte random string and converts it to hexadecimal, perfect for a JWT secret. Copy this generated string and paste it into our .env file as the JWT secret value. Great! Now let's get our Gemini API key. This is what will power our AI recipe generation. Open your browser and go to Google AI Studio. Once you're in Google AI Studio, you'll need to sign in with your Google account if you haven't already. Click on Get API Key in the left sidebar. Then click Create API Key. We'll see a pop-up here. Again, click the Create Key button. Perfect. Google has generated our API key, so make sure to copy it now. Click the Copy button to copy our API key. Now go back to VS Code and paste this API key into our .env file as the Gemini API key value. Excellent. Our environment is now fully configured with all the necessary credentials. Now let's create our main server file. We'll open up server.js and start building our basic Express server. First, we want to load our environment variables, so at the very top we'll import .env and immediately configure it. This makes everything inside our .env file available through process.env. Now let's bring in the rest of our dependencies. Great! Next, we initialize our Express application. Now we'll configure our middleware. This allows our front end to communicate with our backend without cross-origin issues. Next, we'll parse incoming JSON. This allows us to read JSON request bodies. And we'll also handle URL encoded data. This is useful for form submissions and other encoded payloads. Nice, our middleware is set up. Now let's add a simple test route to confirm everything works. So whenever we visit the root URL, our server responds with a simple JSON message. Just something lightweight to verify the server is running. Now we define our port. We'll default to port 8000 if nothing is defined in our environment variables. And now we start listening. Now we'll test everything. Nice, the server is running on port 8000. Let's open the browser and navigate to the Test API endpoint. And there it is. Our backend server is officially up and running. Now that we have our server running, let's set up our database and build the authentication system. First, let's create our database configuration file. This will handle the connection to our Neon PostgreSQL database. Navigate to the config folder and create a file called db.js. Now let's set up our database connection pool. We're importing the PostgreSQL client and extracting the pool class. The pool manages multiple database connections efficiently. Now let's create our connection pool. This creates a pool using our Neon connection string from the .env file. We enable SSL for secure connections. Neon requires this. Let's add some event listeners to monitor our connection. These listeners help us debug connection issues during development. Finally, let's export our database interface. Perfect. Now we can import this DB object anywhere and run queries. Now let's create our database schema. This defines all the tables we need for our application. Create a file called schema.sql in the same config folder. First, we'll enable the UUID extension for generating unique IDs. Now let's create our users table. This stores our user accounts with email, hashed password, and name. Notice we're using UUIDs instead of auto-incrementing integers. This is more secure and scalable. Next, the user preferences table. This stores each user's dietary preferences, allergies, and cooking preferences. The text array type is a PostgreSQL array, perfect for storing lists. Now the pantry items table. This tracks what ingredients users have in their pantry, including quantities and expiry dates. Let's create the recipes table. This table stores each recipe with its metadata like name, difficulty, prep time, and servings, while linking it to a specific user through a foreign key. Notice we're using JSON-B for instructions. This lets us store structured cooking steps efficiently. Now the recipe ingredients table.
This creates a many-to-many relationship between recipes and ingredients. Let's add the nutrition table. This table stores nutritional values like calories, protein, carbs, fats, and fiber for each recipe, linked through a foreign key. The unique of recipe ID constraint ensures each recipe can only have one nutrition record, maintaining a strict one-to-one relationship. Now the meal plans table. This lets users plan their meals for the week. The check constraint ensures meal type is always valid. And finally, the shopping list table. This table stores individual shopping list items for each user, including ingredient name, quantity, unit, and optional category. Boolean flags like is checked and from meal plan help track purchased items and whether they were generated from a meal plan. Perfect. Now let's add some indexes for better query performance. These indexes will make our queries much faster, especially as the database grows. Now let's create a function to automatically update the updated at timestamp. And let's create triggers to use this function. These triggers automatically update the updated at column whenever a row is modified in their respective tables. Excellent. Our schema is complete. This will automatically keep track of when records are updated.
Now we need a way to run this schema and create all our tables. Let's create a migration script. In the Backend root folder, create a file called migrate.js. Let's start with our imports, load our environment variables, create a database pool. Now let's create the migration function. This migration function connects to the database, reads the schema.sql file, and executes all SQL statements in one run to create the tables and triggers. It also includes proper error handling and connection cleanup to ensure the process exits safely whether the migration succeeds or fails. Finally, let's run the migration. Great, now let's test it. In our terminal, run this command. Excellent. All of our tables have been created and the database is ready to use. To confirm, let's also check the Neon project dashboard. Open your project, then click on Tables in the left sidebar menu. Perfect. As you can see, all of our tables have been successfully created. Now let's create our user models. These will handle all database operations for our entities. Navigate to the Models folder and create user.js. First, import our dependencies. We'll use bcrypt to hash passwords securely. Now let's create our user class. This creates a new user with a hashed password. Notice we're using parameterized queries. This prevents SQL injection attacks. Let's add a method to find users by email and find by ID. Notice we're not returning the password hash for security. Let's add an update method. Coalesce only updates fields that are provided, perfect for partial updates. Now let's add password management methods. The update password method securely hashes the new password using bcrypt before storing it in the database, ensuring raw passwords are never saved. The verify password method compares a plain text password with the stored hash to authenticate users safely without exposing sensitive data. And finally, a delete method to delete the user record from the table. And we will export the class. Perfect, our user model is complete. Now let's create the user preferences model. Create userpreferences.js in the models folder. This model will handle storing and managing each user's personalized settings in the database. First, let's import the database. This allows us to execute SQL queries using our shared database connection. Next, let's define our class and add an upsert method. Now, what we're doing here is destructuring the preferences object and setting default values, just in case some fields are missing. Then we're using PostgreSQL's onConflict clause, which essentially turns this into an upsert. In other words, if a record for this user already exists, we update it, otherwise we insert a new one. As a result, each user will always have only one preferences record, and we can safely update it anytime.
Now that we can create or update preferences, let's also add a method to retrieve them. Here, we're simply selecting the preferences based on the user ID. And importantly, if no record exists yet, we return null instead of throwing an error, which keeps our application logic clean and predictable. Finally, let's add a delete method. With this method, we can remove a user's preferences entirely if needed. For example, this could be useful if a user resets their settings or deletes their account. And to wrap everything up, let's export the class. This way, we can import and use this model inside our controllers or routes. Perfect. Now we have our user model and our user preferences model ready to go. Next, we can connect everything together and start handling real user data in our application.
All right, before we jump into building our controllers, we first need to set up authentication middleware so we can protect our routes. So let's navigate to the middleware folder and create a new file called auth.js. First, we'll import JWT. This package will allow us to verify and decode the tokens we generate during login and registration. Now let's create our middleware function. So here's what's happening. First, we extract the token from the authorization header. We're expecting it in the format bearer token, so we remove the bearer part. Next, if no token is provided, we immediately return a 401 response, meaning access is denied. Then we verify the token using our JWT secret. If it's valid, we decode it and attach the user information to rec.user. Finally, we call next so the request can continue to the protected route. Now let's export it. And just like that, we now have middleware that can protect any route in our application. Now that our middleware is ready, let's move on and build our authentication controller. This will handle registration, login, and token generation. So let's navigate to the controllers folder and create authcontroller.js. First, we'll import our dependencies. Here, we're importing our models and JWT so we can create users, manage preferences, and generate tokens. Before writing our controller functions, let's create a small helper function to generate JWT tokens. So what we're doing here is signing a token that contains the user's ID and email. Additionally, we're setting it to expire in 30 days, which keeps users logged in but still maintains security. Next, let's implement our register function. So first, we extract the email, password, and name from the request body. Then, we validate the input to make sure all required fields are provided. After that, we check if a user already exists with the same email. If so, we return an error. Otherwise, we go ahead and create the new user. Immediately after creating the user, we also initialize their default preferences using our user preference model. Finally, we generate a token and return both the user data and the token in the response. Now let's implement the login function. Here, we start by validating the input. Then we attempt to find the user by email. If the user doesn't exist, we return an error. Next, we verify the password using our model's password verification method. If the password is valid, we generate a new token and return it along with the user's basic information. Finally, let's add a function to get the currently authenticated user. Since this route will be protected by our auth middleware, we already have access to rec.user, so we simply fetch the user from the database using that ID and return the result. All right, next, let's add a password reset request function. Now, in a real production application, this would actually send an email with a reset link, but for now, we're just creating a placeholder endpoint. So first, we extract the email from the request body. Then we validate it to make sure the client actually provided an email address. If not, we return a 400 error. Next, we attempt to find the user by email. However, and this is very important, we do not reveal whether the user exists or not. Instead, we always return the same success message. Later on, in a real-world setup, this is where we would generate a reset token and send a password reset link via email. But for now, this gives us the correct structure and keeps our API secure. Great! Now our authentication controller handles registration, login, fetching the current user, and even password reset requests. All right, now that our authentication logic is complete, let's move on to building our user controller for profile management. So we'll head over to the controllers folder and create a new file called usercontroller.js. First, let's import our models.
We'll be using the user model to manage account data and the user preference model to handle preference-related updates. Let's start by creating the getProfile function. So here's what we're doing. Since this route will be protected by our auth middleware, we already have access to request.user. First, we fetch the user's basic account information, then we fetch their preferences using the same user ID. Finally, we return both pieces of data together in a single response, which makes it easy for the front end to load the full profile in one request. Next, let's add the updateProfile function. Here, we extract the updated name and email from the request body. Then we call our model's update method, passing in the current user's ID. After that, we return the updated user data along with a success message. This keeps our response consistent and predictable across the API. Now let's handle updating preferences. Instead of writing separate create and update logic, we're using our upsert method again. So whether preferences already exist or not, this will handle both cases automatically. As a result, our controller stays clean and simple. Next, let's add password change functionality. So first, we validate that both the current and new passwords are provided. Then we verify that the current password matches what's stored in the database. If it doesn't match, we return an error. However, if it is valid, we proceed to update the password securely. This ensures users can only change their password if they truly know their existing one. Finally, let's implement account deletion. Here, we simply delete the user based on their authenticated ID. Once completed, we return a confirmation message. In a production environment, we might also handle cascading deletes or soft deletes, but structurally, this gives us everything we need. Excellent. Now our user controller is fully complete. We can retrieve profiles, update account details, manage preferences, change passwords, and even delete accounts. Next, let's wire everything together by setting up our authentication routes. So we'll navigate to the routes folder and create a new file called auth.js. First, let's import our dependencies. Here, we're creating a new Express router instance. Then we're importing all of our authentication controller functions along with our auth middleware, which we'll use to protect certain routes. Next, let's define our public routes. These routes do not require authentication. So, for example, users need to be able to sign up and log in without already having a token. Additionally, the reset password request should also be accessible publicly. Each route simply maps an endpoint to the corresponding controller function. Now, let's define a protected route. Here's where our middleware comes into play. Before the request reaches getCurrentUser, it first passes through auth middleware. If the token is valid, the request continues. However, if the token is missing or invalid, access is denied. This ensures that only authenticated users can access their own profile information. Finally, let's export the router. This allows us to import and use these authentication routes inside our main server file.
All right, now let's set up our user routes. So we'll head over to the routes folder and create a new file called users.js. First, let's import our dependencies. Here, we're creating a new router instance. Then, we're importing all of our user controller functions. And of course, we're bringing in our auth middleware because all user-related routes should be protected. Now, since every user route requires authentication, instead of attaching the middleware to each route individually, we can apply it once to the entire router. This means every route defined below this line will automatically require a valid JWT token. Clean and efficient. Now, let's define our routes. So here's what we're doing. We fetch the user profile, we update profile details, we update preferences, we allow password changes, and finally, we allow account deletion. Since we already applied auth middleware, all of these routes are fully protected. Finally, let's export the router. And just like that, our user routes are ready. Now we need to connect everything to our main server. So let's open server.js. We already imported our routes at the top, so let's scroll down to where we mount them. You'll see something like this. Perfect. This means all authentication routes are prefixed with API/auth. All user routes are prefixed with API/users. Everything is now properly structured and mounted. All right, now for the fun part. Let's test everything. First, make sure our server is running. Great! Our server should now be running on port 8000. Now let's test the signup endpoint. I'll use Thunder Client, but you can use Postman or any API client. Create a new post request to /API/off/signup. Send the request. Perfect. We got a 201 response with our user data and a JWT token. The user was created successfully. Now let's test login. Create a post request to /API/off/login. Send it. Excellent. We got our token back. Login works perfectly. Now let's test a protected route. Copy the token from the response. Create a GET request to /API/users. Add an authorization header. Send the request. Perfect. We got the user profile and preferences. Our authentication system is working flawlessly.
All right, now let's quickly verify that our data was actually inserted into the database. So we'll head over to our Neon dashboard and open our project. Next, let's click on Tables in the left sidebar and then select the Users table. And there it is. We can see the newly created user record. We have the generated UUID, the email alex@timetoprogram.com, the hashed password, the name Alex, and the created and updated timestamps. Notice that the password is not stored as plain text. It's securely hashed, which means our authentication system is working properly. And just like that, we've confirmed that our signup endpoint is successfully writing data to the database. Perfect. Everything is connected and working exactly as expected. Now we're going to build the core features of our AI recipe generator, the pantry management, recipe handling, meal planning, and shopping list functionality. These are the features that make our app truly useful. Let's dive in. First, let's build the pantry management system. This lets users track what ingredients they have at home. Navigate to the Models folder and create pantryitem.js. Import our database connection. Now let's create the pantry item class with a create method. This creates a new pantry item with all its details: name, quantity, unit like cups or grams, category like vegetables or dairy, expiry date, and whether it's running low. Now let's add a method to get all pantry items with optional filters. This is a dynamic query builder. We start with the base query, then add filters based on what the user wants to see. The I like operator does case-insensitive searching, perfect for finding ingredients by name. We're building the query dynamically to avoid SQL injection while keeping it flexible. Let's add a really useful method, finding items that are expiring soon. This helps users know what ingredients they need to use soon, reducing food waste. We're using PostgreSQL's interval to add days to the current date, super handy for date calculations. Now let's add the standard CRUD operations, find by ID. Notice we always include the user ID in our where clause. This ensures users can only access their own data. Security is built right into our queries. Let's add update method. Again, using coalesce for partial updates, only the fields provided will be updated. Now let's add delete method. And finally, a stats method to show pantry overview. This gives us a nice dashboard overview: total items, how many categories, items running low, and items expiring soon. The filter clause is a PostgreSQL feature that lets us do conditional counting in a single query, much more efficient than multiple queries. Don't forget to export. Perfect. Our pantry model is complete. Now let's build the recipe model. Since recipes connect to ingredients and nutrition stored in separate tables, we're designing this model to orchestrate multiple relationships in one clean flow. Create recipe.js in the Models folder. Import the database. This gives us direct access to our connection pool so we can execute queries and manage transactions safely. Let's create the recipe class with a create method. This one is special because it needs to insert into 3 tables: recipes, recipe ingredients, and recipe nutrition. So instead of running separate independent queries, we wrap everything inside a transaction to keep our data perfectly in sync. So first, we explicitly begin the transaction, which tells our database that everything after this point must succeed together. Then we insert the main recipe record and capture the returned row so we can use its ID for related inserts. Next, we dynamically build the ingredient insert statement so we can handle any number of ingredients efficiently in a single query. After that, we conditionally insert nutrition data only if it exists, keeping our database clean and flexible. Finally, we either commit everything if it works or roll everything back if something fails, ensuring our data integrity is never compromised. Notice how we stringify the instructions before saving them. Since they're stored as JSON-B, we make sure the structure is preserved exactly as we designed it. Now let's add a method to get a complete recipe with all its related data. Instead of returning partial information, we assemble the full picture of the recipe in one structured response. First, we verify the recipe belongs to the correct user for security and data isolation. Then we fetch ingredients and nutrition in separate queries to keep our schema normalized and clean. Finally, we merge everything together using the spread operator so our controller receives one complete, easy-to-use object. Next, let's build a powerful search method with multiple filters. Instead of hard-coding queries, we dynamically construct them based on the filters provided. Initially, we start with a base query that joins nutrition so calorie data is readily available in list views. Then, step by step, we append conditions only if corresponding filters exist, which keeps our queries efficient and flexible. Additionally, we safely parameterize everything to prevent SQL injection while dynamically tracking parameter positions. Finally, we add sorting and pagination so our API remains scalable even when the dataset grows large. The any operator is especially powerful here because it allows us to check whether a dietary tag exists inside an array column cleanly and efficiently. Now let's add a method for recent recipes. Instead of building another complex filter system, we keep this focused and optimized for display dashboard. Here, we simply sort by creation date descending so the newest recipes appear first, which makes this perfect for our dashboard overview section. Now for the update method. Instead of forcing full updates, we allow partial updates using coalesce, which makes our API much more flexible. By using coalesce, we ensure that only provided fields get updated while everything else remains untouched, which keeps our updates safe and predictable. Next, let's implement delete. Instead of manually cleaning related tables, we rely on our schema design to handle cascading behavior. Thanks to our cascade delete configuration, removing a recipe automatically removes its related ingredients and nutrition, keeping our database consistent without extra logic. Finally, let's add stats. Instead of calculating metrics in our application layer, we let the database efficiently aggregate everything for us. Here, we compute total recipes, cuisine diversity, and average cooking time in one optimized query, which keeps our analytics fast and scalable. Finally, export the class. And with that, our recipe model is fully structured, transactional, filterable, and production-ready, meaning our backend now has a solid foundation to handle complex recipe data cleanly and efficiently.
Now let's create the meal planning system. Instead of just storing recipes, we're now connecting them to specific calendar dates so we can organize our cooking schedule day by day. Create mealplan.js in the Models folder. Import the database. This gives us access to our database connection so we can read and write meal plan entries efficiently. Now let's create the class with a create method. Rather than blindly inserting records, we'll use an upsert pattern so our system behaves intelligently when a meal already exists for a given slot. First, we normalize the date field so whether the front end sends planned date or meal date, our back end handles it consistently. Then, instead of throwing an error when a duplicate entry exists, we use onConflict to update the recipe for that meal slot automatically. Additionally, we cast the date explicitly to ensure it's stored as a proper SQL date, which prevents subtle time zone or formatting issues later. This makes our meal planner flexible, clean, and user-friendly. Next, let's add a method to retrieve meals within a specific date range. Instead of requiring multiple front-end calls, we'll join recipe data directly into the result. Here, we join the recipes table so we can immediately return the recipe name, image, and cooking times along with the meal plan entry. Then we sort first by date and second by meal type using a case statement so breakfast always appears before lunch and dinner. Finally, we cast the date to text to make JSON serialization straightforward and consistent for our API responses. As a result, our front end gets everything it needs in one efficient query. Now let's build a weekly meal plan method. Instead of rewriting logic, we'll reuse our existing date range function. First, we calculate the end date by adding 6 days to the starting date, giving us a full 7-day window. Then, rather than duplicating SQL logic, we delegate to find by date range, which keeps our code dry and maintainable. This approach ensures any improvements to our date range logic automatically apply to weekly planning as well. Next, let's implement a method to get upcoming meals. This is especially useful for dashboards and quick previews. Here, we filter meals starting from current date, so only future or current meals are returned. Then, just like before, we sort them logically by date and meal type to maintain consistent ordering. Finally, we apply a limit so we can control how many meals appear on our dashboard without overwhelming the UI. This keeps our homepage fast and focused. Now let's add the delete method. Instead of soft deleting, we're permanently removing the entry, keeping the planner clean and straightforward. Notice how we include user ID in the condition to guarantee users can only delete their own meal plan entries, which reinforces our data security model. Finally, let's compute some meal planning stats. Instead of calculating counts in JavaScript, we let the database handle aggregation efficiently. Here, we compute the total number of planned meals as well as how many fall within the upcoming week. By using a filtered count, we efficiently calculate both metrics in one query, which keeps our analytics fast and scalable. Finally, export the class. And just like that, our meal planning system is fully integrated, allowing us to assign recipes to calendar dates, retrieve weekly schedules, show upcoming meals, and generate meaningful planning statistics with clean, reusable logic.
Now, let's build the shopping list model. Unlike our other models, this one connects meal plans, recipes, and pantry inventory, so we're essentially building automation that turns plans into actionable grocery lists. Create shoppinglist.js in the models folder. Import the database. This gives us access to both direct queries and transaction control through the connection pool. Now let's create the class with the most powerful method, generating a shopping list from meal plans. Instead of manually adding items one by one, we're automating the entire grocery workflow. First, we begin a transaction to ensure the entire generation process runs atomically. Then we clear previously generated meal plan-based items so we don't duplicate data across runs. Next, we aggregate ingredients from all planned recipes using sum and group by, which consolidates duplicate ingredients automatically. After that, we load pantry items into a map so we can perform O of 1 lookups instead of inefficient nested loops. Finally, we subtract pantry quantities and only insert items that are actually needed, making our shopping list smart and optimized. This is where our application truly becomes intelligent instead of just CRUD-based. Now let's add a method to manually add items. Not everything comes from meal plans, so we keep the system flexible. Here, we default the category and explicitly mark from meal plan as false, so we can distinguish manual entries from generated ones later. Next, let's retrieve all shopping list items. Instead of returning random order, we sort them for usability. By ordering first by category and then by ingredient name, we make the list predictable and easy to scan.
Now let's group items by category directly in PostgreSQL. Instead of transforming data in JavaScript, we leverage database-level JSON functions. Here, JSON AG and JSON build construct nested JSON directly in the database, which reduces backend processing and keeps our API responses clean and front-end ready. Next, let's implement update. Instead of forcing full replacements, we support partial updates using coalesce. This keeps our API flexible while ensuring users can only update their own items. Now let's add a clean toggle method. Instead of sending true or false explicitly, we flip the Boolean directly in SQL. The not operator instantly inverts the Boolean, making this both simple and elegant. Now let's implement delete. Instead of soft deletion, we permanently remove the item. Including user ID in the condition ensures proper data isolation. Next, let's clear only checked items. Instead of wiping everything, we target completed purchases. This allows users to quickly clean up their list after shopping. Now let's add a full clear option. Sometimes users want to reset everything. This removes all items regardless of status. Finally, here's another powerful automation, adding checked items directly to the pantry. Instead of manually re-entering purchases, we streamline the workflow. First, we start a transaction to guarantee consistency. Then we retrieve all checked items and insert them into the pantry table one by one. After successfully adding them, we remove them from the shopping list so the workflow feels seamless. If anything fails, we roll everything back so no partial updates occur. Finally, export the class. And just like that, our shopping system is fully intelligent, automatically generating grocery lists from meal plans, subtracting pantry inventory, organizing items by category, and syncing purchased items back into pantry storage.
Now let's create our pantry controller code. First, let's move into our controllers folder and create a new file called pantrycontroller.js, because this is where all the logic for handling pantry-related requests will live. Import the model. Here, we're bringing in our pantry item model so we can interact with the database from inside our controller. Now, let's create our function to fetch pantry items. So first, we extract our query parameters from the request. Then we pass those filters into our model to fetch only the items that match. Notice how we convert the string true into a Boolean, because query parameters always come in as strings and we need to normalize them before passing them down to our data layer. Next, let's build a function to return pantry statistics. Here, we simply delegate the heavy lifting to our model by calling getStats with the current user's ID. In other words, our controller stays clean and focused on handling the request and response cycle while our model handles the data logic. After that, let's handle items that are about to expire. This time, we parse the days query parameter and default to 7 if none is provided. Then we pass that value into our model method so we can dynamically control how far ahead we check for expiring items. Now let's implement the create functionality. Here, we pass the authenticated user's ID along with the request body to our model's create method. Additionally, we return status 201, which means created, and that clearly communicates that a new resource has been successfully added to our system. Moving on, let's allow users to update an existing pantry item. First, we grab the ID from the route parameters, then we attempt to update the item for that specific user. If nothing is returned, we send back a 404 not found, because that means the item either doesn't exist or doesn't belong to this user, and that's proper RESTful error handling. Finally, let's implement the delete functionality. Once again, we extract the ID, attempt the deletion, and verify whether an item was actually removed. If not, we return a 404 to keep our API consistent and predictable. Otherwise, we confirm the successful deletion in our response. Our pantry controller is fully wired up. Each function clearly handles one responsibility, keeps our code organized, and cleanly connects our routes to our model layer. Now, let's move into our controllers folder and create recipecontroller.js, because this is where we'll handle everything related to recipes, including our AI-powered generation. Import our dependencies.
Here, we're importing our recipe and pantry item models for database operations, and in addition, we're pulling in our Gemini AI utilities so we can delegate smart generation logic to a dedicated layer. Now, let's build the heart of this controller, AI recipe generation. First, we destructure and assign defaults from the request body so our function is resilient even if some fields are missing. Then, if use pantry ingredients is true, we fetch all pantry items for this user and merge them with the provided ingredients. Notice how we wrap everything in a set. This automatically removes duplicates, ensuring our AI receives a clean, unique ingredient list before we finally call our Gemini generation function. Next, let's generate AI-powered suggestions based on pantry contents. Here, we first fetch all pantry items and then specifically retrieve items expiring within 7 days. After that, we extract just the names of expiring items and pass both the full pantry list and prioritized expiring names into our AI utility so it can intelligently suggest recipes that help reduce food waste. Now, let's allow users to persist recipes. In this case, we pass the authenticated user's ID along with the request body to our model's create method. Additionally, we return HTTP 201, which clearly communicates that a new recipe resource has been successfully created in our system. Next, let's implement flexible filtering and pagination. Here, we extract all possible filters from the query string and carefully convert numeric values like max cook time, limit, and offset into integers. This ensures our model receives properly typed values and prevents subtle bugs caused by string-based comparisons in our database queries. Now, let's return only the most recent recipes. This time, we default the limit to 5 if none is provided, which gives us sensible behavior out of the box while still allowing flexibility when the client wants more or fewer results. Next, let's fetch a single recipe. First, we extract the recipe ID from the route parameters and attempt to find it for the current user. If nothing is returned, we respond with a 404 because that means the recipe either doesn't exist or doesn't belong to this user, and that's proper RESTful error handling. Now, let's support updating existing recipes. Again, we grab the ID, attempt the update scoped to the current user, and check whether a record was actually modified. This conditional check ensures we don't silently succeed when the resource doesn't exist. Finally, let's implement the delete functionality. Just like before, we attempt the deletion and verify that something was actually removed. If not, we return a 404, maintaining consistency across all our endpoints. And finally, let's expose recipe statistics. Here, we simply call into our model's getStats method and return the results, keeping our controller thin and focused purely on orchestrating the request response flow. This completes our recipe controller, combining traditional CRUD operations with AI-powered intelligence while keeping responsibilities cleanly separated between controller, model, and utility layers.
Now let's create the AI utility file. Navigate to the Utils folder. Inside Utils, create Gemini.js. Let's start with imports. We're importing the Gemini SDK and .env to access our API key. Now initialize the Gemini client. This creates our AI client and warns us if the API key is missing. Always good to have helpful error messages. Now for the exciting part. Let's create a function that generates complete recipes using AI. Good documentation is important. This JS doc tells us exactly what parameters the function expects. Now let's build the dietary restrictions text. This creates a human-readable string from the dietary restrictions array. If there are none, we say so explicitly. Let's add a cooking time guide. This maps our simple time categories to more descriptive text for the AI. Now comes the critical part, crafting the perfect prompt. This is where the magic happens. This is a carefully crafted prompt. We're being very specific about what we want, a JSON response with exact fields. Notice how we're asking for structured data that matches our database schema perfectly. Now let's call the Gemini API.
We're using the Gemini 2.5 Flash model. It's fast and great for structured outputs. The response comes back as text, so we trim any white space. Sometimes AI returns markdown code blocks, so let's handle that. This strips out markdown formatting if the AI includes it. We're using regex remove the code block markers. This makes our function robust. Now parse the JSON. We parse the cleaned text as JSON and return it. If anything goes wrong, we catch the error and throw a user-friendly message. Next, let's create a function that suggests recipes based on what's in the user's pantry. This function is smart. It prioritizes ingredients that are expiring soon. Build the ingredients list. We extract just the names from pantry items and highlight expiring ingredients. This helps reduce food waste. Create the prompt. This is a simpler prompt. We just want quick suggestions, not full recipes. Call the API. Same pattern as before. Call the API and get the text. Clean up Markdown. Parse and return. Perfect. This gives users instant inspiration based on what they already have. Let's add one more helpful feature: AI-generated cooking tips for any recipe. Now let's build the prompt. We're using optional chaining operator here. If ingredients don't exist, we won't get an error. Defensive programming. Call the API. Notice the graceful fallback. If the API fails, we return a generic but helpful tip instead of crashing. Always think about user experience. Finally, let's export all our functions. This allows us to import these functions in our controllers. We already used these AI util functions in our previous controller code. Now let's build the controller layer that connects our routes to the meal plan model. Create mealplancontroller.js inside the controllers folder. Import the model so we can delegate all database logic cleanly. Now let's implement the method that assigns a recipe to a calendar date. Instead of writing SQL here, we delegate directly to the model's create method. The controller's job is simple: pass the authenticated user ID and request payload, then return a structured response. Notice how we rely on rec.user.id instead of trusting the client. This reinforces our security model by ensuring users can only create meal plan entries under their own account. We also return a consistent JSON structure with success, message, and data, which keeps our API predictable for the front end. Next, let's retrieve a full week of meals. Rather than forcing the front end to use a single rigid parameter name, we support both start date and week start date. This makes our API flexible without complicating our logic. First, we normalize the input so both parameter names resolve to a single start date variable. Then, instead of allowing invalid requests to proceed, we guard early with a 400 response. Once validated, we delegate to get weekly plan, keeping the controller thin and focused. Now let's add support for dashboards and quick previews. Instead of hard-coding a fixed number of meals, we allow a limit query parameter. If none is provided, we default to 5, a sensible number for a homepage widget. This keeps our endpoint flexible while maintaining performance control. The front end can request more items if needed, but we avoid overwhelming the UI by default. Next, let's handle deletion. Rather than deleting blindly, we pass both the meal plan ID and the authenticated user ID to the model. This ensures users can only remove their own entries. If no record is returned, we respond with a 404. This makes our API explicit and predictable. Consumers always know whether an operation succeeded. Finally, let's expose planning analytics. Instead of calculating totals inside the controller, we delegate aggregation entirely to the model. The controller simply returns the result. This keeps our controllers lightweight and focused on request-response flow, while the database handles performance-intensive calculations. And just like that, our meal plan controller is complete. Finally, let's move on to the shopping list controller and connect our ingredient workflow to the rest of the system. Create shoppinglistcontroller.js inside the controllers folder. Import the model so the controller remains focused on request-response handling. Just like before, we keep database logic inside the model and let the controller orchestrate behavior. This keeps our architecture clean, layered, and easy to maintain. Let's start by generating a shopping list directly from a selected meal plan range. Rather than requiring the front end to manually collect ingredients, we let the back end derive everything from the meal plan between two dates. First, we validate the required dates to prevent unnecessary database work. Then, we delegate to the model, passing the authenticated user ID to ensure data isolation. This allows users to instantly convert their weekly plan into a ready-to-use shopping list. Next, let's retrieve the shopping list. Instead of forcing a single response format, we support both grouped and flat data structures using a query parameter. If grouped equals true, we return items organized by category, perfect for section-based grocery store navigation. Otherwise, we return a flat list. This small design choice makes the API flexible without adding complexity. Now let's allow manual additions. Rather than limiting the list to generated items, we give users the ability to add custom entries. Again, notice how the authenticated user ID is always passed from the backend, not the client. This guarantees ownership and prevents cross-user access. Next, we enable editing existing items. Instead of assuming the record exists, we handle the possibility that the item may not be found. This keeps our API explicit and predictable. If the item doesn't belong to the user or doesn't exist, we return a clear 404 response. Now let's make the list interactive. Instead of manually updating a Boolean field on the front end, we expose a dedicated toggle endpoint. This keeps state transitions centralized and prevents inconsistent client-side logic. Next, we support permanent removal. By always scoping queries to rec.user.id, we maintain strict user-level isolation across every operation. Now let's optimize cleanup. Instead of deleting items one by one, we provide a bulk operation that removes all checked items at once. This makes post-shopping cleanup fast and efficient. Similarly, we allow users to reset their entire list. Rather than requiring multiple delete requests, one endpoint handles everything cleanly. Finally, let's connect shopping to inventory. Instead of manually re-entering purchased items into the pantry system, we automate the transition. This creates a seamless workflow: meal plan to shopping list to pantry. Each step builds on the previous one, reinforcing a cohesive system design. Excellent! Our controllers are now fully implemented. Now let's wire up the routes and connect everything to our API layer.
Navigate to the Routes folder and create Pantry.js. First, import our dependencies. Instead of protecting each route individually, we apply authentication once at the router level. This guarantees every pantry endpoint requires a valid authenticated user, clean, centralized, and secure. Now let's define the routes. Notice the order. Specific routes like /stats and /expiring soon come before parameterized routes like /id. If we reverse this order, Express would interpret stats as an ID, which would cause incorrect routing behavior. Finally, export the router. Our Pantry API layer is now clean and predictable. Next, create recipes.js inside the routes folder. Import dependencies. Again, protect everything at the router level. Now define the routes. First, we group AI-related endpoints. Separating AI functionality from CRUD operations keeps the structure intentional and easier to scan. Next are core recipe routes. Again, specific routes like recent and stats appear before /id to prevent routing conflicts.
Export the router. Now let's configure meal planning routing. Create mealplans.js inside the routes folder. Import dependencies. Protect all routes. Define the endpoints. We intentionally place /weekly, /upcoming, and /stats before any parameterized routes to avoid collisions. Export the router. Meal planning is now fully exposed through our API. Finally, let's wire up the shopping list. Create shoppinglist.js in the routes folder. Import dependencies. Protect everything. Now define the routes. Route ordering is subtle but critical in Express applications. Export the router. Now let's add the API routes in our server.js file. Open server.js and scroll top and add the route imports. And at the bottom, add the routes. Each domain is isolated under its own API namespace. This keeps our backend modular, scalable, and easy to reason about. And just like that, the entire backend is fully wired. Controllers handle orchestration, models handle data logic, routes handle HTTP structure. Everything is layered, secure, and cleanly organized. Now our API is production ready and ready to power the front end.
Now let's test a few of our new endpoints to make sure everything is working correctly. First, let's test adding a pantry item. Create a post request to API/pantry. Next, we'll add the authorization header with our JWT token. Now we'll send a JSON body containing the pantry item details, including its name, quantity, category, expiration date, and stock status. Now send it. Perfect. We received a 201 created response, which means the item was successfully added to our pantry. To verify, let's head over to our Neon PostgreSQL dashboard, navigate to the Pantry Items table, and there it is. Our item has been successfully inserted into the database. Next, let's retrieve all pantry items. Create a GET request to API/pantry. Make sure we include the same authorization header. Now send it. Excellent. We can see our tomatoes in the response, which confirms our retrieval endpoint is working correctly. Now let's test our recipe endpoint. Create a post request to API/recipes. Here, we're sending a complete recipe object, including metadata, cooking instructions, ingredients, dietary tags, and nutrition information. Now send it. Amazing! The recipe was successfully created, including all ingredients and nutrition data. Once again, let's verify in our Neon PostgreSQL dashboard by navigating to the Recipes table. And there it is. Our recipe is successfully linked and stored in the database. Everything is working correctly. Authentication, database relationships, and API responses are all functioning as expected. Now that our backend is fully verified, let's move on to the front end and start integrating these APIs to bring our application to life.
Now that our backend is complete, let's connect our front end to real APIs. Right now, our Boilerplate project is purely UI-based. It looks complete, but it's powered entirely by dummy data. Authentication doesn't actually talk to a server, it just simulates a logged-in user. Let's fix that. We'll start with the most important piece, the auth context. Open the existing auth context. In the Boilerplate version, we import a dummy user. Inside useEffect, we automatically log in with that dummy user.
And our login and register functions don't make any API calls. They simply set local state. This is perfect for UI development because it lets us design the interface without worrying about backend connectivity. But now we're replacing simulation with real authentication. Before rewriting the context, let's quickly look at API.js. This file creates a centralized Axios instance. Instead of calling Axios directly throughout our app, we use this configured instance. Why? Because it gives us a single base URL, automatic JSON headers, centralized interceptors, and consistent error handling. Here's where it gets powerful. Instead of manually attaching the token in every API call, this interceptor automatically injects the authorization header if a token exists. That means every authenticated request works seamlessly. We also handle token expiration globally. If the backend returns 401, we immediately clear the stored token, clear the stored user, redirect to login. This keeps our authentication flow secure and consistent without duplicating logic across components. This is production-grade front-end architecture. Now let's update auth context. Instead of importing dummy user, we import our API instance. In the boilerplate version, we auto-logged in with dummy data. Now, instead of faking login, we check if a real token exists. Rather than assuming a user exists, we restore authentication state from local storage. This ensures page refresh doesn't log the user out, authentication persists across sessions, and we avoid unnecessary API calls on startup. Now let's replace the simulated login with an actual API call. Instead of instantly setting state, we now send credentials to the backend, receive a token and user object, store both in local storage, and update global auth state. Notice we don't manually attach the token to future requests. The interceptor handles that automatically. That's clean separation of concerns. Now let's implement registration. So instead of creating a fake user locally, we now create the user in the database, immediately receive a token, log them in automatically, and persist their session, which makes onboarding seamless. No extra login step needed. Now for logout. Since we're using stateless JWT authentication, we don't actually need to tell the backend anything. We just remove the token client-side. And that's enough. At this point, authentication is wired in auth context and our backend is live. Now we'll connect our login and signup pages to that context and explain how the flow works end to end. So let's start with the login page. Go ahead and open login.js. Right away, we can see this component is mostly UI, and that's intentional. We've kept the design layer clean and separate from business logic. Our login page doesn't need any changes. Let's understand why it already works. The handle submit function code works perfectly because it calls login from our auth context. Our updated auth context now makes the API call. It handles success or failure with toast notifications, navigates to dashboard on success. The beauty of this architecture is that we only had to update the auth context. The UI components didn't change at all. Same story with signup.js. Here, the handle submit function just works. The separation of concerns, UI versus logic, makes our code clean and maintainable. Let's test everything. Make sure our backend is running. And start our front end. Now let's open our browser and navigate to login page. From here, click on Sign Up button and let's fill the form. We'll enter a name, email, and password. Before clicking on Create Account button, let's open the Network tab in the DevTools. Now let's click on Create Account button. Watch the Network tab in DevTools. We see the post request to signup endpoint and the response with user data and token, and our page redirects to dashboard. Let's also check local storage. We'll see the token and user saved, and it redirects to dashboard.
From here, click the Logout button. Now, here in the login page, let's fill the form and click on the login button. Watch the Network tab in DevTools. We see the post request to login endpoint and the response with user data and token, and our page redirects to dashboard. Let's also check local storage. We'll see the token and user saved, and it redirects to dashboard. While logged in, if we refresh the page, we should stay logged in. This works because our use effect checks local storage on mount. Amazing work! We've successfully integrated authentication. Now, let's start by updating our navbar to show the logged-in user's information with a nice drop-down menu. Navigate to Components folder and open navbar.jsx. First, let's add the React hooks imports. Now, let's add state for the dropdown. We are tracking whether the dropdown is open and using a ref to detect clicks outside. Update the logout handler to close the dropdown. Now, let's add a click outside handler. This is a common pattern. We add a global click listener and check if the click was outside our dropdown. The cleanup function removes the listener when the component unmounts. Now, let's replace the simple logout button with a user profile dropdown. Find the user menu section and replace it with this. Beautiful. We're showing the user's first initial in a circular avatar, their name, and a chevron that rotates when the dropdown opens. The chain operator safely handles cases where user data might not be loaded yet. This is the dropdown menu. It shows the user's full name, email, and a logout button. Now, let's check the UI in the browser. Perfect. We have a user profile dropdown that shows the user's full name, email, and a logout button. Now, let's connect the dashboard to our backend APIs. This is where things get exciting. Open dashboard.jsx. First, update the imports. We're removing the dummy data import and adding our API service. Update the state to include loading. Now, replace the use effect with a real API call. This is beautiful. Let me explain what's happening. Promise.all. We're making 5 API calls in parallel. This is much faster than making them sequentially. All calls complete at roughly the same time. Destructuring. We're destructuring the responses directly from the promise.all array. Optional chaining. The logical OR operator provides fallback values if the API returns null or undefined. Finally block. This runs whether the try succeeds or fails, ensuring loading is always set to false. Now add a loading state before the return. This shows a nice spinning loader while data is being fetched. The AnimateSpin class from Tailwind makes it rotate. The rest of the dashboard component stays the same. It already renders the data correctly. Now let's test the dashboard in the browser. Perfect. We have a loading state and the data is being fetched correctly. We can see the stats section that shows the total number of recipes, pantry items, and meals this week. We can also see the recent recipes and upcoming meals section that show the last 5 recipes and the next 5 meals.
Now for the most complex integration, the pantry page with full CRUD operations. Open pantry.jsx. Update the imports. We're removing dummy data and adding our API service. Update the state to include loading. Now replace the use effect with real API calls. Add the fetch functions. The fetch pantry items function fetches all the items from the pantry, and the fetch expiring items function fetches the items that are expiring soon. Notice we're using query parameters days equals 7 to specify how many days ahead to check for expiring items. Now, update the delete handler to call the API. We're using template literals to include the item ID in the URL. After successful deletion, we update the local state to remove the item immediately. This gives instant feedback. Add a loading state. The rest of the pantry component, filtering, UI, stays the same. Now let's update the add item modal to actually save to the backend. Find the add item modal component and update the handle submit function. This handle submit function makes a post request to backend with the form data and converts the quantity to a number with parse float. It also sets the expiry date to null if it's empty, an optional field.
After successful addition, it calls onSuccess to refresh the pantry list and closes the modal. Now update the onSuccess callback in the pantry component. When an item is added, we refetch both the pantry items and expiring items to keep everything in sync. Now let's test the pantry page in the browser. Perfect. We have a loading state and the data is being fetched correctly. We can see the pantry items and the expiring items sections that show the last 5 items and the next 5 items. We can also add a new item to the pantry by clicking on the Add Item button and filling in the form. The item will be added to the pantry and the pantry list will be updated immediately. We can also delete an item from the pantry by clicking on the Delete button next to the item. The item will be deleted from the pantry and the pantry list will be updated immediately. Perfect. Our pantry page is now fully functional with CRUD operations.
Now let's start with the most exciting feature, the AI recipe generator. Navigate to Components folder and open recipegenerator.jsx. First, let's update the imports to use our API service. We're removing the dummy data import and adding our API service. Now let's update the use effect to fetch real user preferences. When the page loads, we automatically fetch the user's saved preferences from their profile. If they've set dietary restrictions like vegetarian or a preferred cuisine like Italian, those options are pre-selected. This saves them time. Now let's update the handle_generate function to call the real AI API. Let me break down what's happening. Validation. We check if the user has either added ingredients manually or checked Use Pantry Ingredients. At least one is required. Request payload. We send all the user's preferences to the backend. Ingredients, the manual ingredients they added. Use pantry ingredients, whether to use their pantry items. Dietary restrictions like vegetarian, gluten-free. Cuisine type, the selected cuisine or any. And servings and cooking time, their preferences. The backend takes these inputs, queries the user's pantry if needed, and sends everything to OpenAI's GPT model. The AI generates a complete recipe with ingredients, instructions, nutrition info, and cooking tips. State updates. We set the generated recipe in state and show a success toast. The finally block ensures generating is set to false whether the request succeeds or fails. Now let's update the handle save recipe function. Perfect. When the user clicks Save Recipe, we extract all the fields from the AI-generated recipe and save it to the database. Notice we're mapping the camel case fields from the front end to snake case for the backend API. The saved recipe will now appear in the My Recipes page. Now let's test the Generate Meal flow in the browser. Open the browser and navigate to the pantry page. Here, we already have some ingredients added. We have garlic, bell pepper, chicken, tomatoes. Let's add some more ingredients. Let's add potatoes, onions, and some spices like turmeric, chili powder, cumin powder, coriander powder, salt, and oil. Now go to the Generate Recipe page. Here, let's start with the Ingredients section. First, we have this checkbox that says Use Ingredients from my pantry. When we check this, the AI will automatically include all our pantry items when generating the recipe. Below that, we can manually add additional ingredients. Now let's select Preferences. We'll select Italian cuisine type, gluten-free dietary restriction, 4 servings, and medium cooking time. Click on Generate Recipe button. It will take some time to generate the recipe. Once the recipe is generated, it will be displayed in the results panel. And here is the generated recipe. At the top, we have the recipe name and a short description. Below that, we have badge tags and step-by-step instruction. Each step is numbered with an emerald circle, making it super easy to follow along while cooking. Next, we have the nutrition information per serving displayed in a grid: calories, protein, carbs, fats, and fiber. This is really helpful for people tracking their nutrition. We can save this recipe to our collection by clicking on the Save button. Let's save the recipe by clicking on the Save Recipe button. Perfect! Our Generate Meal feature is working as expected. Now let's move on to the next feature. Now let's connect the My Recipes page to display all saved recipes. Open myrecipes.jsx. Update the imports. Add a loading state that will be used to display a loading spinner while fetching recipes. Update the use effect to fetch recipes from the API. Add the fetch recipes function. Simple and clean. We fetch all recipes for the current user. The backend automatically filters by user ID using the JWT token. Now update the handle delete function. We're using optimistic UI updates again. After the delete request succeeds, we immediately filter out the deleted recipe from the local state. The user sees instant feedback. Add a loading state before the return. The rest of the component stays the same. The filtering logic, search, cuisine, difficulty, is all client-side, so it works without any changes. Now for the recipe detail view with dynamic servings adjustment. Open recipedetail.jsx. Update the imports. We remove dummy data imports and add API import. Add a loading state. Update the use effect to fetch recipes from the API. Add the fetch recipe function. We're using the ID from the URL params from React Router to fetch the specific recipe. If the recipe isn't found or there's an error, we redirect back to the recipes list. Update the handle delete function. After adjust quantity, let's add a loading state. If the recipe is loading, display a loading spinner. The rest of the component stays the same. The servings adjuster, ingredient checkboxes, and all the UI logic work perfectly without any changes. Now let's test the My Recipes page and Recipe Detail page. Open the browser and navigate to the My Recipes page. Great, now we can see all recipes we have saved. To delete any recipe from the list, use the Delete button. This will delete the recipe from the list. Now click on the recipe to view the recipe details. This will take us to the Recipe Detail page. Great, now we can see the recipe details. Now click on the servings adjuster and adjust the servings. You should see the ingredient quantities adjust accordingly. Perfect, now let's check our Neon dashboard to verify the database changes. Open the Neon dashboard and navigate to the recipes table. We should see the recipes saved. The pantry table should also have the ingredients we added. Recipe ingredients table should also have the ingredients used in the recipe. Recipe nutrition table should also have the nutrition information of the recipe.
Let's start with the meal planner. This component lets us plan our meals for the week. It contains a calendar view of the week and allows us to add meals to the calendar. Now let's open mealplanner.jsx. Update the imports to include the API service. We are removing the dummy data and adding our API service. Next, update the component state to include a loading state. Update the use effect to fetch data when the week changes. We will remove the load meal plan function call and replace it with fetch meal plan and fetch recipes function calls. Now let's implement the fetch meal plan function. This function calculates the start and end dates of the current view, Monday to Sunday, and fetches only the relevant meals from the backend. Then it organizes them into a nested object organized of date and meal type, which makes rendering the grid much easier. We also need fetch recipes, so users can select from their saved recipes. Now implementing the deletion logic, we will remove the local state logic and instead use the API service to delete the meal plan. Notice we properly await the API call and then refresh the meal plan. Finally, we need to update the add meal modal component at the bottom of the file to actually save the meal. This function is called when we add a new meal to the meal plan. It takes the selected recipe, planned date, and meal type as parameters and sends a post request to the API to create the new meal plan. It also shows a toast message to notify the user of the success or failure of the operation. Finally, it calls onSuccess function to refresh the meal plan. It's all the changes we need to make to the meal planner component. Next up is the shopping list. This is one of the most interactive parts of the app. Open shoppinglist.jsx. Update imports to include the API service. Add loading state inside the shopping list component. Inside the use effect, remove the load shopping list function call and replace it with fetch shopping list to fetch data when the component mounts. Now let's implement the fetch shopping list function.
Here in the function fetch shopping list, we are fetching the shopping list from the backend and organizing it by category. The backend returns items already grouped by category, but we flatten them in state to make updates like checking or unchecking easier, then regroup them for display. Let's implement the checkbox toggle, remove the local state change code, and instead use the API service to toggle the checkbox. We use optimistic UI updates here, but wait, actually we are calling the API first. For a checkbox, you might want to switch this to optimistic, update state first, then call API, to make it feel instant. Now the delete function. This function is called when we delete an item from the shopping list. It takes the ID of the item to be deleted as a parameter and sends a delete request to the API to delete the item. It also shows a toast message to notify the user of the success or failure of the operation. Finally, it calls organize by category to refresh the shopping list. Now let's update the clear checked items function. This function is called when we clear all checked items from the shopping list. It takes no parameters and sends a delete request to the API to clear all checked items. It also shows a toast message to notify the user of the success or failure of the operation. Finally, it calls organize by category to refresh the shopping list. And now the add to pantry feature. This is really cool. This endpoint takes all checked items, moves them to the pantry table in the database, and removes them from the shopping list. It's a huge time saver for users. Also, at the bottom, update the add item modal to use the API. This function is called when we add a new item to the shopping list. It takes the form data as a parameter and sends a post request to the API to add the item. It also shows a toast message to notify the user of the success or failure of the operation. Finally, it calls onSuccess function to refresh the meal plan. Lastly, let's add a loading state to the shopping list. Finally, let's complete the settings page. This handles user profile updates, dietary preferences, and account management. Open settings.jsx. Update imports to add the API service. We need states for loading and saving. Now let's update the use effect to fetch the user data on mount. Remove the load user data function and add the fetch user data function. The fetch user data function is called when the component mounts and fetches the user data from the API. It then updates the profile and preferences states with the fetched data. Finally, it sets the loading state to false. Now let's update the handle profile update function. This function is called when we update the profile. It takes the form data as a parameter and sends a put request to the API to update the profile. It also shows a toast message to notify the user of the success or failure of the operation. Now let's update the handle preferences update function. This function is called when we update the preferences. It takes the form data as a parameter and sends a put request to the API to update the preferences. It also shows a toast message to notify the user of the success or failure of the operation. Now let's update the handle password change function. This function is called when we update the password. It takes the form data as a parameter and sends a put request to the API to update the password. It also shows a toast message to notify the user of the success or failure of the operation. Now let's update the handle delete account function. This function is called when we delete the account. It takes the form data as a parameter and sends a delete request to the API to delete the account. It also shows a toast message to notify the user of the success or failure of the operation. That's it for the settings component. Now let's test the meal planner, shopping list, and settings pages in our browser. Let's open the browser and navigate to meal planner page. Perfect. We can see our calendar grid. Each cell in the grid represents a meal slot. Empty slots show a plus icon that we can click to add a meal. For slots that already have meals planned, we see the recipe name in an emerald box. When we hover over a planned meal, a delete button appears to remove it from the plan. Let's add a meal to our plan. I'll click on the plus icon for Monday breakfast. A modal pops up showing Add Meal with the date and meal type. Let's select one of our recipes and click Add Meal. Excellent. The meal is now added to our calendar. We can see it displayed in the Monday breakfast slot. Let's add a few more meals to our week to make it more complete. Great! Now we have several meals planned throughout the week. At the bottom of the page, we have stats showing meals planned, total recipes available, and the current week range. Now let's test the shopping list page. Let's navigate to Shopping List page. Perfect. Here we can see the shopping list items are displayed grouped by category. We can check off items as we shop, and there's a delete button to remove items. We can add items to the shopping list using the Add Item button. This is useful for non-recipe items like snacks or household supplies. At the top, we have action buttons to clear checked items or add checked to pantry. The Add Checked to Pantry button is really useful. It takes all the items we've checked off and automatically adds them to our pantry, then removes them from the shopping list. This creates a seamless workflow from shopping to cooking. Finally, let's check out the Settings page. Here we can see our name and email fetched and displayed in the Profile tab. We can only update our name from here. Then we have Change Password section where we can update our password by providing the current password, new password, and confirm password inputs. The Preferences tab allows us to define our default dietary restrictions, preferred cuisines, and serving size. These settings are automatically applied to the recipe generator form, so each time we create a recipe, the fields are pre-filled based on our tastes. This streamlines the process and makes generating personalized recipes faster and more convenient. And finally, the account deletion, danger zone. This is a critical feature, so we add a double confirmation. First, a standard browser confirm dialog. If they say yes, we use a prompt to ask them to type delete to confirm. This pattern is common in critical actions to prevent accidental deletions. Once confirmed, we call the API to delete the user and all their associated data, recipes, meal plans, etc., thanks to the cascading deletes in our database schema. Then we log them out and redirect to the login page. Clean and safe. And that is a wrap on our AI recipe generator journey. We have successfully built a full-stack application using the PERN stack, PostgreSQL, Express, React, and Node.js. We've covered everything from database design and authentication to AI integration and complex state management. Use this project as a launchpad for your own ideas. Add social sharing, image generation, or nutritional tracking. The sky is the limit. Thank you so much for watching. See you in the next one. Happy coding!